Hello everyone, my name is Stefan. My background is in parallel computing and scientific computing, and I'm with CARIAD. This is the newly founded software organization within the Volkswagen Group. I'm responsible for the data aggregation system of our customer fleets. This is what Volkswagen and CARIAD calls the big loop. This system is spawning from technologies in the vehicle up to technologies running in the data center and the cloud. Today, I would like to tell you about the big loop system. The key design objective of that system is not to gather a vast amount of data, but to gather the data which provides the most relevant information and the highest value for customer feature development. Before I justify that statement, I would like with you to zoom back a little bit and show you what our teams are currently working on. Currently within CARIAD, we are developing a unified and scalable next generation architecture, which we call E-Cube 2.0. There, our teams are working on numerous different layers of that architecture. On the hardware layer, on the operating system layer, which is called the VWOS, and also the layer which runs in the cloud, which we call automotive cloud, the VWAC. And obviously also on the customer-facing application layer. There, one of our key focus areas is assistant and automated driving. We strongly think this will become a key value driver for the Volkswagen Group in the future. Within that domain, you all know about classical data acquisition. There, vehicles are equipped with a high-cost setup of storage technology in the trunk. Then, these vehicles are sent to distinct campaigns where data is aggregated on the road. Every bit of data which is streamed through the sensors is recorded. And finally, on a daily basis, physically offloaded into some central storage location. We are currently working on the next generation of this technology. We are currently limiting the outdated method where we record every bit of data and work towards a method where we can greatly reduce the amount of data, yet being able to sustain the level of extracted information out of that data. Moreover, we would like to take it to the next level and even have the data recorded from this technology instantaneously available for our engineers. Within this challenge, our teams are expanding rapidly. If you are passionate and skilled in the following areas, please do not hesitate to contact me. Currently, we're focusing on machine learning, data science, parallel computing, scientific computing, data engineering, and obviously all the applications towards the automotive world. I and my team would be super happy to get in contact with you. But let me show you now what are the key building blocks of the next generation architecture where the big loop is built on. Let's focus on the hardware layer. The hardware layer is a distributed system with a zonal topology. In the core of that topology, there sits a so-called scalable compute platform. Within the SCP, there is one distinct compute host for all the ADAS AD full driving stack functionality. This we call the ADAS blade. The ADAS blade has a sibling. This is called the protected area blade. This sibling is, by the hardware layer, protected from any interference from the rest of the system. With this, we can assure highest safety standards, yet using the protected area for development purposes. Furthermore, the hardware layer also provides a concurrent access to all the data streamed throughout the vehicle, from raw sensor data down to signal data. Due to the freedom of interference of the hardware layer, we are able to update the protected area from the layer of the operating system upwards on a very high frequency. And this is giving us basically a very efficient engineering tool. The protected area itself caters two main purposes with respect to the big loop. The first one is shadowing. Shadowing means I take a pre-release of software, monitor it under real-world conditions, and I'm really able to see how this release candidate software is performing on the real world. The second application of the protected area is that we can leverage the compute power of the protected area blade for doing intelligent data aggregation and collection. All those in-vehicle components, they live in symbiosis with the components which are run inside the cloud. These two worlds together, the data center and the cloud and the in-vehicle stuff, is forming the big loop system. But let us zoom in now and follow the data. Let us start inside the protected area. Here, a deep neural network-based software component, which we call Instinct. This is an acronym for In Situ Intelligent Data Collector. This piece of software analyzes in real time all the data streamed throughout the vehicle. And it can tell on the basis of uncertainty and out of distribution samples which kind of data samples are of interest to us. Once such a sample is detected, a snapshot of that data is then preserved within a non-volatile storage within the SCP. Once the vehicle has cellular connection, then we can ingest that data into the cloud. Depending on the data and the use case, the big data stack which is operated on the cloud can work in batch or streaming mode. Once the data has arrived through the ingest pipeline and is persisted inside the data lake, we are able to use multiple different consumption pipelines in order to actually leverage the information out of that data. It is also possible, if needed, to seamlessly blend not just machine learning techniques, rather than also things around the virtual world like simulation and replay into the game. With such collected data, the customer feature increment is developed, and after testing and validation, sent via online remote update to the customer. On the same time, we make sure that Instinct is also updated and has the same level of information where it's built on as the full driving stack. With this, we are really able to come up with an end-to-end active learning loop for the entire vehicle software development process. This is what we call data-driven development. Let us have now a closer look into the technology. For instance, for the use case of vision-based perception, Instinct is looking out for known and unknown unknowns. So you might ask, what is an unknown unknown? As you see here, a vehicle is running through the environment. Here it's seeing a pedestrian, here it's seeing vehicles, everything it was trained for. Suddenly there comes a pink elephant. It has never seen that pink elephant before. So what Instinct is capable of is a so-called unknown unknown detector. That means, with respect to the elephant, that it does not need to know to look out for pink elephants. It can judge about that by means of uncertainty. And you can now tell me, a pink elephant, this is a nice story, yet what has that to do with ADAS AD, for example? Let's now take the pink elephant and bring it to the real world. Let's assume we would like to build a real-world feature. Let's assume we want to build a traffic light assistant. Within this scenario, Instinct is watching out for interesting scenarios around traffic lights. As you see, Instinct is computing uncertainty matrix, in this example here, pixel-wise. Based on those metrics, it is able to judge which kind of images or image sequences are of interest to us. Then these images are sent to the cloud and to the big data stack. Yet you might argue, is that wishful thinking? Well, I'm super proud today to show you an exclusive preview on the road of a very early release of our system. Here you can see a holistic version of the system on the road, where a vehicle in California is currently running on the road, and Instinct is looking out for interesting scenarios around traffic lights. Another remarkable item which I would like to point out is that we can run Instinct in the vehicle and also in the cloud. This enables our engineers that they can accelerate the development velocity of Instinct. Assume Instinct has now collected enough data. This data can be used for multiple different purposes. Let's assume, coming back to our traffic light assistant example, there we would use that data for training a perception module, which is at the final end able to be one of the key building blocks of this traffic light assistant feature. Once we have aggregated that data, as you know, this data needs to be enhanced. Why? Because we would like to deploy supervised learning techniques for our perception model, which is a part of the traffic light assistant feature. In order to do that, we can use semi-automatic or even pseudo-labeling pipelines. This depends highly on the use case, if it's a single image or if it's a video feed, etc. At that level, we have then data which we actually can use for training. In our example, we would then train the perception module, which is a part of the traffic light assistant. This training would undergo again a smaller loop, as you are aware. Once the so rendered artifact has been verified through virtual testing, and it has been verified that the data which is aggregated throughout the Instinct and the big loop has met the design targets, we could then use a first release candidate of the traffic light assistant feature. Then this can now be released to the protected area and tested and scaled under real-world conditions. After the successful completion of engineering and the beta testing, the new enhanced customer feature or even a version of Instinct can then be downloaded to the vehicles. With this, the big loop has been completed once. So you might ask now, what's next? There is still one challenge to work on. The challenge is not in the technology. It is about how we develop our products. As you know, the normal product release cycle within automotive industry is kind of different than what you would see for software world. It means to bring an automotive vehicle to the world takes way longer than the software. In order to bridge that, our teams have developed a system which can be retrofitted to the already existing vehicles and platforms. Based on that effort, we are currently ramping up a so-called pioneering fleet. which means that we can achieve a sufficiently high scaling of the big loop system prior to the start of the production of the next generation architecture. This is key, as we believe, to tame the long tail issue, one of the key problems of automated driving. Moreover, this allows the teams to overcome the challenge to use DevOps for in-vehicle automotive software development. This is because this very long classical product release cycles. Thus, the plan forward is to seamlessly grow and mature the features and the system of the big loop, and ultimately bring that system from the pioneering fleet seamlessly into the next generation architecture and then to the entire product portfolio of the Volkswagen Group. So stay tuned and contact me if you have passion to help us to scale it and bring it alive. I'm strongly convinced the big loop and the pioneering fleet are key to tame the long tail issue for automated driving. And at the final end, this will enable us to really leverage end-to-end active learning and continuous data-driven development throughout the vehicle software design process. This will help to provide even safer, more sustainable, and more comfortable rides for you as our end customers. I would like to thank you very much today that you took the time to come with me through the journey of Big Loop. And now I'm super happy to answer your questions.